Today we are going to learn about Venn diagrams. And Venn diagrams can be effectively used to show the event relationships. For example, there are events N and event B contain their respective outcomes, and the shaded regions indicate the event relation of each diagram. So this is the typical example for the Venn diagram, including the event A and event B. And this is normally called the sample space. And this is the event A, and this is the event B. So what is the intersection of event A and event B? This is the sample space, and this is the event A, and this is the event B. In this case, the intersection of the event A and event B will be this shaded region, okay? And what is the intersection of the union of event A and event B and event C? In this case, we have one more event, right? Event C. Firstly, we have to consider about the union of event A and event B. There will be this zone, right? That is the union of event A and event B. And the intersection of the union of event A and event B and event C will be this part, right? So this is the intersection of the union of event A and event B and event C. And what is the complement of the intersection of event A and event C? So to calculate the complement for this equation, we have to know about the intersection of event A and event C. That is the first step. And what is the intersection of event A and event C? There will be this part, right? So the complement of this part will be this shaded area, okay? So that is the complement of the intersection of event A and event C. So we can easily see the relationship of the event by using the Venn diagram. And if the event A and B share no common outcomes, they are considered to be mutually exclusive. 상호 배타죠, in Korean. So this is the schematic description of this case. And this is the sample space. And this is the event A and event B. And as you can see, there is no connected area between the event A and event B. So the occurrence of one event A precludes the occurrence of the other event B. So symbolically, this can be expressed by this relationship. The intersection of the event A and event B equals to the null set, which is called 공집합. And this is the symbol for the null set. And now we are going to discuss about the event relations relation laws. Firstly, the event order is unimportant. And this is the typical example. And as you can see, the intersection of the event A, event B equals to the intersection of the event B and event A. And also, the union of event A and event B equals to the union of event B and event A. So based on this relationship, we can simply think that the event order is unimportant. And there is also distributive law. And based on the distributive law, the intersection of the union of event A, B, and C can be expressed by a different relationship. Based on the distributive law, the first equation can be expressed by the union of the intersection of the event A and C and the intersection of the event B and event C. So this is the same equation with this one based on the distributive law. And also, this equation can be changed to this is the intersection of the union of A and C and the union of B and C. So this relationship can be simply calculated based on this relationship, based on the distributive law. And there is also De Morgan's law. And based on the De Morgan's law, we can express these two equations in different equations. For example, for the first equation, this is the complement of the union of event A and event B. And this can be expressed by the complement of event A and intersection and the complement of event B. That is the De Morgan's law. And also, the bottom equation can also be expressed as the complement of event A union the complement of event B. So I will verify the first relationship here. That is the first relationship for the De Morgan's law, right? So we can first think about this equation first here. This is the sample space. And this is the event A, this is the event B. So to calculate the complement of the union of event A and B, we have to first know about the union of A and B, right? The union of A and B will be this, right? And the complement of the union of A and B will be this shaded area. And that is the complement of the union of A and B. And now I'm going to express the right equation based on the Venn diagram. And in this case, we have to first know about the complement of event A. So what is the complement of event A? In this case, that will be this shaded area, right? And what is the complement of event B? that will be this shaded area. So if we have an intersection between these two relationships, we can finally have this shaded zone, right? That will be the complement of event A intersection the complement of event B. So as you can see, the shaded area is equal to the previous case. So the De Morgan's law can be used for calculate some event relationships. And this is about the counting techniques. There are three special rules or counting techniques used to determine the number of outcomes in the event and the sample space. First one is the multiplication rule, which is called 곱셈 법칙 in Korean. And the permutation rule, which is called 순열 법칙 in Korean. And also, there is a combination rule, which is called 조합 법칙. And each has its special purpose, and they must be applied properly. Firstly, I'm going to explain about what is the multiplication rule. And based on the multiplication rule, N1 indicate the number of ways of completing step 1, and N2 indicate the number of ways of completing step 2, blah, blah, blah. And Nk indicate the number of ways of completing step K. Then the total number of ways to complete all of the steps from 1 to K will be N1 multiplied by N2 multiplied by Nk. And the reason why we can obtain this relationship can be explained in this example. And this is the example 2-9 for the multiplication rule. And in the design for a gear housing, we can use among 4 different fasteners and 3 different bolt lengths and 2 different bolt locations. So in this case, how many designs are possible? We all learned about the tree diagrams, right? So based on the tree diagrams, we can firstly have the type of fastener, right? And also, there is a bolt length. And also, there is a bolt location. So in this case, we have 4 different types of fasteners. And we can simply denote that as type 1, type 2, type 3, type 4. Okay? So in that case, we can also have 3 different bolt lengths, such as long, medium, short. So we have 3 more options here. There will be long, medium, and short. And the long can be expressed as L, and medium can be expressed as M. The short can be expressed as S. And we can have 3 different bolt lengths at each location, right? So we have L, M, S, L, M, S, L, M, S. Then we have 2 bolt locations. So there are 2 different cases. First one is, for example, left, and the other one is right. We have 2 more options. And this can be applied to all these points, right? So in this case, the total number of outcomes can be simply calculated by, this is the 4, this is the 3, this is the 2, based on the multiplication, right? So this will be 24. So the total number of outcomes for this case can be simply calculated by the multiplication rule rather than using this tree diagram. Now we are going to discuss about the permutation rule. And a permutation is a unique sequence of distinct items. If a set of elements S include A, B, C, then there are 6 permutations. Why? The permutations of the sample S will be A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Right? So this is the permutation of the event S, including A, B, C items. So the number of permutations for a set of n items is n factorial. So this is the equation for the factorial function. If there is an n factorial, that will be equals to n multiplied by n minus 1, multiplied by n minus 2, blah, 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 multiplied by 2, and multiplied by 1. That is the equation for the factorial function. And if we consider about this space, this element, the number of permutations will be 3 factorial, right? Why? The number n is 3, A, B, C. So this will be 3 multiplied by 2 multiplied by 1, right? So this will be 6. So that is the number of permutations. Okay? And now we know about the 3 factorials. So based on the permutation, we can also calculate the permutations of subsets. So in the previous case, we only have a set. But in this case, we have a subset in a set. This is the set. This is the subset. Okay? So in this case, we want to calculate the number of permutations from this subset. Okay? And this is the example to explain about the number of permutations in a subset. And this is about the circuit board design. Circuit board is called Peropan in Korean. And a printed circuit board has 8 different locations in which a component can be placed. So this is the circuit board having 8 different holes, okay? And if 4 different components are to be placed on the board, how many designs are possible? 8 is the number of elements in the set, right? And we can have 4 choices to be placed on among these 8 holes, right? So in that case, 4 is the number of subset, right? So based on the permutation equation, the number of designs can be calculated by the permutation of A and 4, okay? So this will be 8 factorial divided by 8 minus 4 factorial. And this equals to 8 multiplied by 7 multiplied by 6 multiplied by 5 multiplied by 4 factorial divided by 4 factorial. So the 4 factorial will be eliminated each other. And finally this will be, this is 30, this is 210. 1,680 designs can be made for this case, okay? So this is a typical example for the permutations of a subset. And now we are going to think about the permutations of similar objects. And this can be used for counting the sequences when each item is identical. The number of permutations for n equals to n1 plus, n2 plus, and blah, 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 plus nr items of which n1 are identical, n2 are identical, and nr also are identical. In this case, we can calculate the number of permutations by this equation. N factorial divided by n1 factorial multiplied by n2 factorial multiplied by nr factorial. This can be understood based on this another example. And this is the example 2-11 for the machine shop schedule. In a machine operation, a piece of sheet metal leads to 2 identical diameter holes and 2 identical size notches. So the drilling operation is denoted as D, and the notching operation is denoted as N. So in this case, how many sequences can be obtained? In this case, we have 4 elements, right? 2 drilling operations and 2 notching operations. But the drilling operations is identical, right? And the notching operation is also identical. So we have total 4 elements, and the n can be calculated by the summation of n1 and 2, and in this case, n1 is 2 drilling operation, and this is the 2 notching operation. But n1 has the same object, drilling operation, and also n2 has same object, notching operation. So in this case, we can calculate the number of sequences by this equation, n factorial divided by n1 factorial multiplied by n2 factorial. And this will be 4 factorial divided by 2 factorial multiplied by 2 factorial. Okay? And this will be 4, 3, 2 factorial and 2 factorial multiplied by 2 multiplied by 1. So the 2 factorial can be eliminated each other, and these 2 can be eliminated by dividing 4 by 2. So the total number of sequences can be 6. Okay? And the 6 sequences are summarized as, we denote D as drilling operation, right? And also we denote N as notching operation. So in this case, we can have the drilling operation at the first time and at the second time, right? And then we can have the notching operation at the third time and first time, right? And also, we can have D, N, D, N, right? N, D, N, N, D, right? And also, N, D, N, D, N, N, D, D, N, 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 D, D. And this is all that we can obtain from this example, right? So as you can see, the total permutations will be 1, 2, 3, 4, 5, 6. Okay? So we can simply calculate it, the permutations of similar objects based on this equation. Okay? Now, we're going to have a different example to explain about the permutations of the similar object. And we all know about the barcode, right? A part is labeled by printing with 4 thick lines, 3 medium lines, and 2 thin lines. We have 4 thick lines. Three medium line and 2 thin line. And in this case, the total number of elements will be 4 plus 3 plus 2, 9, right? So N is 9. And as I mentioned previously, N can be separated into 3 parts. And this will be N1, and this will be N2, and this will be N3. And each case, they have the same object. In this case, some thickness. So N can be expressed as N1 plus N2 plus N3. And this is the case of the permutations of the similar object, right? So, based on the previous equation, the number of permutations can be calculated by using this equation. N factorial divided by N1 factorial, N2 factorial, and 3 factorials. And this will be 9 factorials, 4 factorials multiplied by 3 factorials multiplied by 2 factorials. Okay? So this can be 9 multiplied by 8 multiplied by 7 multiplied by 6, 5, and 4 factorials divided by 4 factorials multiplied by 3 to 1, and multiplied by 2, 1. So in this case, the 4 factorials will be eliminated each other. And the 3 multiplied by 2 can be also eliminated by 6. And 2 will be eliminated by dividing 8 by 2. This will be 4. So this is 20, 140. So the total number will be 1,216. So by using 4 the same thin lines and 3 medium lines and 2 thin lines, we can have 1,260 different barcodes. So it is very effective to be used in the market. So this is about the permutations of the same object. And now we are going to study about the combinations. A combination is a selection of all items from a set of n where the order is not important. So the main difference between the permutation and combination is the order. In the case of the permutation, we have to think about the order of item, right? Such as ABC or ACB or BAC, something like that. But in this case, we don't have to consider about the order. Why? The order is not important part in the combinations. And this is the example to explain about the combinations. And this is about the number of circuit board design. A circuit board has 8 locations where a component can be placed, as I mentioned previously. And if 5 identical components are to be placed on a board, how many different designs are possible? In this case, we have to think about the identical. When we use the 5 identical components, the order is not important, right? Because we use the same components. So in this case, we don't have to consider about the order. So we can apply the combination rule rather than the permutation rule. The order of component is not important. Why? Because the component is identical. So the combination rule is appropriate. So we can calculate the number of combinations based on the previous equation. The n will be 8, right? This is the total number of elements in a set. The number of locations in a board, right? And there is 5 identical components. There will be all, right? So this can be calculated by 8 factorials divided by 5 factorials multiplied by 8 minus 5 factorials. So this will be 8 multiplied by 7 multiplied by 6 multiplied by 5 factorials divided by 5 factorials multiplied by 3 factorials. And in this case, the 5 factorials can be eliminated each other, and the 3 factorials can be expressed as 3 multiplied by 2 multiplied by 1. And 3 multiplied by 2 is eliminated by the 6. So the total number of combinations will be 56. Okay? So as you can see, even though we increase the number of components as compared to the previous example for the permutation rule, even though we increase the component from 4 to 5, the total number of combinations is decreased because we don't care about the order. 그러니까 순서 고려하지 않으면은 그 컨비네이션 룰 적용하는데 아까는 4개 적용했을 때를 가지고 계산했을 때 1200 얼마 나왔잖아요. 근데 지금 순서를 고려하지 않는 조합을 가지고 오히려 컴포넌트가 하나가 더 늘었음에도 불구하고 조합을 할 수 있는 개수는 훨씬 줄어들었죠. 왜냐하면 순서를 고려 안 해도 되기 때문에. 그만큼 차이가 있습니다. And this is another example. And this is the example 2-14. And in this case, the sampling is generated with a replacement. A total of 50 parts contains 3 defective parts and 47 non-defective parts or good parts. A sample of 6 parts is selected from the total 50 parts with a replacement. And how many different samples are there in the selected 6 parts that contain exactly 2 defective parts? To calculate the number of samples that the selected 6 parts include exactly 2 defective parts can be C of 3, 2. And this will be 3 factorial divided by 2 factorial multiplied by 1 factorial. And this will be 3 multiplied by 2 factorials, 2 factorials multiplied by 1. And 2 factorials can be eliminated. And finally, we can have 3 combinations. Okay? Then, to select the remaining 4 parts from the 47 non-defective parts, how many ways are there? We can apply the same combination rule here, right? So the total number of elements in a set will be 47, and the number of elements in a subset will be 4. And in this case, we don't have to consider about the order, right? So we can apply the combination rule here. This. And this can be calculated by 47 factorials divided by 4 factorials multiplied by 47 factorials. And this can be multiplied by 46 multiplied by 45 multiplied by 44 multiplied by 43 factorials divided by 4 factorials multiplied by 47 factorials. The 47 factorials will be eliminated, and if we calculate this, the total will be 178,365. That is the total number of these combinations. So the total number of subsets can be calculated by the multiplication rule because the two defective parts can be obtained from the 3 defective and the 4 non-defective part can be obtained from the 47 non-defectives. This means that these two cases should be connected with AND condition, not the OR condition, right? Because we can select total 6 parts, but in this case, the 2 parts should be a defective part. So these two conditions should be connected by AND condition. So we can provide the multiplication rule. So the total number of subsets will be C of 3 and 2 multiplied by C of 47 and 4. That will be 3 multiplied by 178,365. And this will be 535,095. So this is the total number of subsets that we can have from the total 50 items. And this is another example. How many ways are there to obtain 6 parts without any requirement from a set of 50? In that case, what is the total number of elements in a set? There will be 50, right? And among 50, we have to select only 6 parts. So the total number of elements in a subset will be 6. But there is no any requirement. That means we don't have to consider about the order, right? So in that case, we can calculate that so in this case, we can eliminate the 44 factorials. And then if we calculate this equation, finally, we're going to have 50,890,700. So this is the total number of the cases that we can obtain 6 parts without any requirement from a set of 50. Okay? So, what is the probability to obtain exactly 2 defective parts and 4 non-defective parts? We can simply divide this by this. Okay? This is the total number of cases that we can select 6 parts without any requirement. That is the total number of items that we can select. And this is the case that we can select 6 parts, including exactly 2 defective parts and exactly 4 non-defective parts. So the probability can be calculated by this, and this will be 535,095 divided by 50,890,700. And if you calculate this, there will be 0.034, and this is 3.4%. Okay? So this is the probability that we can select the sixth part, including exactly to obtain 2 defective parts and 4 non-defective parts. That is the 3.4%. And now I'm going to introduce about the probability. And probability is a chance that a particular outcome of a random experiment will occur. Only finite sample space can be adopted to calculate the probability. And this can be expressed as proportion, as shown in here. For example, 0.15 or 0.5 or 0.25 and etc. And this also can be expressed by percent. For example, 50%. And also, this can be expressed by this fraction. 1 divided by 10 or 3 divided by 20 and etc. So we can have 3 options to express the probability. And also, a probability of 1 indicates certainty. And also, a probability of 0 indicates impossibility. 확률이 1이면은 100%라는 거고 0이면은 전혀 일어날 일이 없다는 얘기죠. 그 얘기입니다. And there are 2 types of probabilities. First one is the subjective probability, which is called 주관적 확률, and is a degree of belief. And this is the example. There is a 50% chance that I will study tonight. But the percent of chance will be changed by my opinion, right? So that is called subject probability, 주관적 확률. And there is also relative frequency, which is called 상대 도수 in Korean. And this is based on how often an event occurs over a very large sample space. And this is a typical example to explain about the relative frequency. And this is the relationship between the voltage and time here. And as you can see, we have 2 corrupted pulses here. The corrupted pulse indicate the pulse with smaller magnitude. And we have total 10 pulses here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 2 corrupted pulses here. So in that case, what is the relative frequency? Relative frequency of the corrupted pulse will be 2 divided by 10. Right? So that will be 20%. So the relative frequency is based on the previous data. So that is the difference with the subjective probability. And now we can think about the equally likely outcomes. Equally likely means 일어날 확률이 동일한 경우, 그러니까 동등한 확률의이라는 뜻이고요. When a sample space consists of n possible outcomes that are equally likely, the probability of each outcomes will be 1 divided by n. So it is very easy to understand because all outcomes have the same possibility. And this is an example. in a batch of 100 balls, only one is colored blue, and only one ball is randomly selected from the batch. This is the example. And in this case, random means each ball has an equal chance to be selected, which is called equally likely. And therefore, the possibility of choosing the blue ball is 1 divided by 100, right? N is, because N is 100 here. And also, it can be expressed by 0.01. And also, it can be expressed by 1%. Because each outcome in the sample space is equally likely. And this is the typical example for the equally likely outcomes about the laser diode. And the laser diode is the machine to make a hole in the steel plate or semiconductor wafers. So by assuming that 30% of the laser diodes in a batch of 100 diodes meet the customer requirements, a diode is selected randomly, which means that each has an equal probability, and each diode has equal chance of being selected. In this case, what is the probability of selecting an acceptable diode which meets the customer requirement? That is very simple, right? We have 30% chance of the laser diode which meet the customer requirement. So we have based on the first sentence, we can simply assume that there are 30 acceptable diodes and 70 non-acceptable diodes. In that case, probability of acceptable diode, we can simply calculate it by this equation, 30 divided by total number of diodes, right? And this will be 30%. And we can simply calculate this by using this equation, but also we can calculate this based on this definition. For discrete sample space, the probability of an event E, which is expressed as PE, equals to the summation of the probabilities of the outcomes in E, which means that what is the probability of selecting one diode? There will be 1 divided by 100, right? And there are 30 acceptable diodes. So total probability can be calculated by the summation of 1 divided by 100, 1 divided by 100, blah, 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 1 divided by 100. And the number of 1 divided by 100 will be 30, okay? So based on this summation, we can simply calculate, we can simply obtain this value, because this value, 30 divided by 100, and this will be 30%. Okay? This is very important concept actually, and the reason why I say this is very important concept will be understood in the later slide. And this is another example for the case of not equally likely. A random experiment has a sample space A, B, C, D here. And these outcomes are not equally likely, which means each case has different probability. And in that case, their probabilities are 0.1, 0.3, 0.5, and 0.1. So we can assume that the event A include A and B, and event B include B, C, D, and event C include D here. And then we can calculate all these things. And I will explain about this. Firstly, we have to express the possibility of each item. And we can simply express this as P right? That is the probability of each element. And then, what is the probability of the event A? Event A include A and B, right? So, the probability of event A will be the summation of the probability of small a and the probability of small b, right? Because event A include A and B. So this will be 0.1 plus 0.3, and that will be 0.4. Okay? And we are going to calculate the probability of the event C here. The probability of the event C will be the probability of D. And that can be 0.1. Okay? So, as I mentioned in the previous slide, this concept is very important. Why? When we want to calculate the probability of an event, we have to know about the probability of each element. And the total probability of the event can be calculated by the summation of each probability. So we know about the probability of the event A will be 0.4 based on the summation of each probability. Okay? Then, what is the probability of the complement of the event A? To calculate this probability, we have to first know about the complement of event A, right? That will be CT, right? So the probability of the complement of the event A will be the summation of the probability of C and the probability of D, right? And that will be 0.5 plus 0.1 equals to 0.6. And also we can calculate the probability of the complement of event B from the same procedure. And also we also can calculate the probability of the complement of event C. And also we can calculate the intersection, union, and intersection based on the same concept. To calculate the probability of some relationship between the event, we have to know about the element included this event. Okay? So we have to first know about the intersection of the event A and event B. and that will be just B, right? Okay? So the probability of the intersection of A and B equals to the probability of small b, and that will be 0.3. And what is the intersection of the event A and event C? There's nothing. So the intersection of event A and C will be null set. So the probability of the intersection of event A and event C will be 0. Okay? 여기까지는 어렵지 않죠. 다 아시는 것들이라 영어라서 좀 어려우신 것뿐이지. So this is the end of today's class, and see you on Friday.